Hello everyone, I'm Mohammad Reza, a PhD student at Umeå University in Sweden, and now I'm going to present our paper, Service Mesh Circuit Breaking from Panic Button to Performance Management Tool. A service mesh is an infrastructure layer comprising a set of configurable proxies to which services connect. Service mesh mechanisms are responsible for load balancing, processing network requests, service discovery, authentication, authorization, and finally, circuit breaking. Circuit breakers provide conditional logic to disallow traffic on a per request level, enabling reactions to overload that are much faster than those achievable through capacity autoscaling. This helps prevent poor performance during load spikes. In a chained microservice architecture, a fault may cascade through multiple layers, which can be prevented by using circuit breakers. But dropping requests for the sake of performance is not a new idea. The challenge is figuring out when to drop a request in a large dynamic distributed systems. This is further complicated by the fact that circuit breaker technologies only allow thresholds to be defined in terms of the number of queued requests or similar metrics that are difficult to map to intuitive measures of service performance, such as response times. Because many factors can affect service performance, even a carefully tuned static circuit breaker threshold can quickly become obsolete. For example, in Istio, we can set a maximum number of requests in the queue of 200 requests. If the queue length exceeds 200 requests, then the circuit breaker rejects other incoming requests. To illustrate the complexity of manually configuring static thresholds for circuit breaking, we present an experiment in which we run a simple application with carefully tuned circuit breaker for good throughput and acceptable tail response times for a service using 2 CPUs in a Kubernetes cluster. In this cluster, despite overload, as you can see in the left chart, we obtain a 95th percentile response time below 500 milliseconds, aligned with good availability, which is not shown. However, according to the right chart, substantially higher 95th percentile response time and poor availability were observed when deploying the same application on another system with one CPU allocation using an identically tuned circuit breaker, even though the workload was scaled down proportionally to the reduced CPU allocation. Similarly, changes to the application itself, which may be frequent due to the wide use of CI/CD pipelines, would also invalidate the tuning of the circuit breaker. To solve the problem of finding the optimal circuit breaker configuration, we define a controller that protects the tail response time by dynamically adjusting circuit breaker queue length threshold and mitigate the failures in the overload. In the service mesh, we are able to monitor all response times and queue lengths of a service, which are the controller inputs. To model the nonlinear relation between the tail response time and queue length, we introduce a simple parameter alpha, that is the ratio of these two. We tune this alpha parameter online through exponential smoothing in order to adapt to changes in workload, server capacity, or server complexity. For the infrastructure of our experiments, we set up 3 virtual machines which have 2 cores of CPU and 4 GB of RAM. We set up the cluster with Kubernetes and Istio. For different system sizes, we use resource limit feature in Kubernetes to use half, 1, and 2 CPUs. We use factorial service. While a factorial service is certainly not a common workload, we chose it since it allows us to experiment with resource demand per request as required to compare our approach in a variety of scenarios. The incoming traffic is generated using the HAOC'21 traffic generator, which selects the think time and the number of users, and maintains a number of client threads equal to the number of users. Each client thread runs an infinite loop that waits for a random time and then issues a request for an item. The random waiting time is chosen from an exponential distribution whose rate parameter is the reciprocal of the think time. The generated traffic scenario is shown here. The experiments were conducted with different numbers of CPUs, different factorial values, and different target response times, giving rise to the 3-dimensional experiment design space shown in the right figure. In this slide, we present our experimental results for response time. It features 9 plots organized in 3 rows and 3 columns. The columns represent allocated CPU cores, specifically half, 1, and 2 cores, respectively. The rows represent application complexity in terms of factorial computed, specifically 5,000, 10,000, and 15,000. All plots have the x-axis time and y-axis 95th percentile response time. Blue is the result from our controller, orange is the result from a static circuit breaker configuration. For each experiment, we emulate the traffic as we see in the traffic scenario. The results for the dynamic and static configurations on different testbeds are shown here. The response times for the static configuration vary widely with the system size and service complexity, whereas the proposed controller maintains the response time below the target value. When the system is underloaded, like when the factorial parameter is set to 5,000, identical results are obtained with the dynamic and static circuit breakers, because the system is not overloaded sufficiently to activate the circuit breaker, but there are some instability in a static configuration in case of half CPU allocation. These results show that our controller successfully maintains acceptable response times in setups with widely varying capacities and applications. In short, the average 50th percentile of the response time distribution for our controller is 4.8 milliseconds, while the static configuration is 112 milliseconds. And the average 95th percentile of the response time distribution for our controller is 49 milliseconds, while for a static configuration is 1263 milliseconds. And now, in this slide, we present our results for the throughput. It features 9 plots organized in 3 rows and 3 columns. The columns represent allocated CPU cores, specifically half, 1, and 2 cores. The rows represent request rates, specifically successful, circuit broken, and failed requests, respectively. All plots have the x-axis time and y-axis request rate. Blue is the result from our controller, and the orange is the result from the static circuit breaker configuration. In this case, the application complexity is held constant by setting the factorial parameter to 10,000, and we emulate the same workload as in the response time experiments. As shown here, our controller yields more successful requests for most system sizes, while the static circuit breaker configuration drops more requests. When the system size is half CPU, there are some failed requests in the static configuration, but not in the dynamic configuration. Our controller thus has negligible effects on throughput. To summarize the results of our experiments, 70% of the requests get served successfully, 29% of requests are circuit broken, and less than 1% of requests fail to get response due to the timeout when using our controller. In contrast, the static configuration obtains an availability of 64%, with 30% of requests being circuit broken and 5% of requests timing out. Here, we present our experimental results for different target response times. It features 3 plots organized in 3 columns. The columns represent different target response times, specifically 50 millisecond, 100 millisecond, 150 millisecond target response time, respectively. All plots have the x-axis time and y-axis 95th percentile response time. Blue is the results for calculation of factorial of 15,000, orange is the factorial of 10,000, and the green is the factorial of 5,000. As shown here, the dynamic configuration generally maintains the 95th percentile response time below 50, 100, and 150 milliseconds independently of the factorial parameter. Also, to study the impact of different workloads on the behavior of the static configuration and the proposed controller, we use a test bed similar to the described before. The results show that workload variation has no impact on the performance of either the static circuit breaker or our dynamic approach. In conclusion, this study applies control theory to circuit breaker design in order to improve application performance and response times. The goal of this work is to design a dynamic circuit breaking mechanism that avoids the problems encountered using current approaches based on a static thresholds configuration. We propose an adaptive controller and evaluate it with over 12 hours of experiments and more than 13 million of requests. Evaluations are performed under various conditions using different system sizes and static configurations. We show that our proposed method can be applied to a black box service and is able to efficiently tune the circuit breaker configuration. As expected, there is a trade-off between response time and throughput, and our controller can easily be configured to optimize this trade-off. And thank you for your time.